All right, so we're in section 6.5, part 2. All right, so last time we came up with this process of multiplying complex numbers in trig form. So we talked about how we put the complex number in trig form, and that that let us do multiplication by multiplying the moduli and adding angles. Well, if we have z equals r cosine theta plus I sine theta. If we want to raise z to the nth power, z to the n is r cosine theta plus I sine theta. And we're going to raise that whole thing to the nth power. And what we're doing here, when we raise a number to the nth power, we're multiplying it by itself. Multiplying it by itself n times. I sine theta times r cosine theta plus I sine theta times dot dot dot. And we're doing that n times. We're just multiplying that number by itself n times. Well, we know that to multiply complex numbers in trig form, we multiply the moduli. Well, if we multiply r times r times r times r n times, what do we get? If we did it 3 times, r times r times r. R cubed, r to 5 times, r to the 5th. So if we do it n times, r times r times r, we keep doing that so many times. We get r to the n. Multiplying something by itself a certain number of times gives us that power. And we know that to multiply complex numbers in trig form, we add the angle. Well, I'm just adding theta to itself n times. So I have theta plus theta plus theta plus theta. What do I get when I do that n times? Theta times n. So it's going to be r to the n cosine n theta plus I sine n theta. So to raise a complex number to the nth power, we raise the modulus to the nth power. That's just a real number to the nth power. And we multiply the angle by n. So this was the example that I talked about last time, where we had some complex number to the 11th power, for example. And I said that was a really difficult problem. Well, now we have a process. Just raise a real number to the 11th power and multiply an angle by 11. Very easy process. This was discovered, worked with by a French mathematician by the name of de Moivre. So this is de Moivre's theorem. Very important theorem in complex numbers. Isn't de Moivre? That's a nice sounding name, de Moivre. All right, so let's look at a quick example of this. Let's say we want to find so before I go to the example, questions on our process here. We just applied what we knew about multiplication to finding powers. So for example, if we wanted to find minus 2 square root 3 minus 2i to the 5th power. This would be a very tedious problem to do. Otherwise, multiplying those parentheses, 5 sets of those parentheses by each other, distributing I squared is -1, combining like terms, lots of work. But now we know the trig form of complex numbers. This is a much easier problem. So we're going to say, we're going to write negative 2 square root 3 minus 2i in trig form. So r is the square root of negative 2 square root 3 squared plus negative 2 squared, which is the square root of 4 times 3, which is 12, plus 4, so square root of 16, which is 4. So our modulus is 4. And tangent theta is negative 2 over negative 2 square root 3, which is negative 1 over square root 3. And what quadrant are we in here? Third quadrant, right? The x and y are both negative. So we need a third quadrant angle whose tangent is negative 1 over square root of 3. So sine has to be 1/2, cosine has, so what is it?
No, did you just say they're both negative?
Oh yeah, they're both negative, thank you. Positive 1 over square root of 3 is our tangent. So we need a third quadrant angle whose tangent, sine has to be 1/2, and the cosine has to be square root of 3 over 2 to get the square root of 3 in the denominator. So what's that angle?
Pi over 6.
Something pi over 6, but we're in the third quadrant.
Just kidding. You're simple.
6 pi over 6 is the y-axis, so 1 more pi 6 gets us down into the third quadrant. That unit circle keeps coming back, reminding you not to forget. Please don't forget. All right, so in trig form, we have negative 2 square root 3 minus 2i is 4 cosine 7 pi over 6 plus I sine 7 pi over 6. So negative 2 square root 3 minus 2i to the 5th is 4 to the 5th times the cosine of 5 times 7 pi over 6 plus I times the sine of 5 times 7 pi over 6. Two to the 5th, any computer people out there know 2 to the 5th power off the top of your head?
Is it 34?
A little too small. 1024.
Oh, yeah, I was way off. Sorry.
120 is getting a little closer. A couple more powers of 2. And then we get the cosine of 35 pi over 6 plus I this times the sine of 35 pi over 6. And then we remember that 35 pi over 6 is coterminal with 35 pi over 6 equals 36 pi over 6 minus pi over 6. 36 pi over 6 is coterminal with 0. So this is the cosine of minus pi over 6 plus I sine minus pi over 6. And now we have a unit circle question again. Cosine of negative pi over 6. Here's pi over 6, negative pi over 6. Square root of 3 over 2. And sine of negative pi over 6. Minus 1/2 I. So we get 512 square root 3 minus 512i. For the 5th power of negative 2 square root 3 minus 2i. All these powers of 2 reminded me of my first computer. Was a Commodore 64. It was called a Commodore 64 because it had 64K of memory.
Wow.
Yeah, 64K.
That's a lot.
Yeah, it was a lot then. All right, questions? So what we're going to do now, now that we have a process of finding powers, the inverse of finding powers is roots. So now we're going to go in reverse to be able to find roots of complex numbers. Something that we've never had the ability to do so far in math. Something that it's like you're going to be like the first people walking on the moon. So nobody's ever done this before. We haven't done it before. All right, so let's talk about roots of complex numbers. All right, so let's use a real number as an example to remember how roots work. We say that if 3 is a 4th root of 81, what that means is 3 to the 4th equals 81. That's what 3 being a 4th root means. That 3 to the 4th power equals 81. Or we could write that as the 4th root of 81 equals 3. These two equations mean the same thing. So what we're going to do is apply this exact same kind of thinking to the powers of complex numbers to figure out how to find the roots of complex numbers. So we're going to do exactly what we've done here and say if, and I'm going to call one of my complex numbers u, because I'm going to call the other one z. If u equals s cosine beta plus I sine beta. And I'm using beta here because my other angle is going to be theta. So if u is an nth root, so some root of z equals r cosine theta plus I sine theta, then that means, just like we talked about here, that s to the nth power equals r. And n times beta has to equal theta, because that's how we find powers. But here I have to keep track of coterminal angles, because it can be equal to theta or any coterminal angle. So I'm going to say plus 2 pi k. This gives us our coterminal angles. So to find powers, we multiply the angle by the power. So that has to equal theta. But we also have coterminal angles. Or what we're interested in is finding the root. So we can go in reverse here and say that s equals the nth root of r, and beta, so we're interested in finding that angle, is theta plus 2 pi k divided by n. Our modulus is just a real number. We can take the nth root of a real number, and we divide our angle by n, but we also have to keep track of these coterminal angles. That's the only wrinkle here, is keeping track of those coterminal angles, but it's pretty easy. So let me consolidate all of this into one statement that gives us an equation about how we're going to find our nth roots. What I was doing here was showing we're going to apply what we know about powers to talk about how we get roots, because powers and roots are the inverses of each other. So if z equals r cosine theta plus I sine theta, the nth root of z is the real nth root of r times the cosine of theta over n, but we're also going to keep track of our coterminal angles, plus I times the sine of theta over n. We're going to keep track of our coterminal angles. And here k, the nice thing about the coterminal angles is eventually they repeat. So we only need to find some of them. K equals 0, 1, 2, dot, 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 up to n minus 1. So for example, if we want to find the third root, k equals 0, 1, 2. If we want to find the fifth root, k equals 0, 1, 2, 3, 4. So we find 3 third roots, 5 fifth roots, 4 fourth roots, 2 square roots. So we take the square root of a real number, we know we get plus or minus, we get 2 roots. Take a third root, we get 3 roots, 4, 5, etc. And usually with these problems, it's going to be easier to do your angles in degrees, and instead of 2 pi k, think 360 k. So we're just adding coterminal angles until those coterminal angles start to repeat. All right, so let's look at an example of finding some roots of complex numbers. Let's find the 4 fourth roots of 16. So we'll talk more about it when we talk about chapter 2 in second semester. But any number has, if we have a fourth root, we have 4 of them. If we have a square root, we have 2 of them. Third root, we have 3 of them. So we need 4 fourth roots. Another way you would be asked this question that's equivalent. Solve. X to the 4th minus 16 equals 0. These are the same because what this is asking us to do is find x to the 4th equals 16, or x equals the 4th roots of 16. So these are 2 ways of asking the same question. You might be asked to solve x to the 4th minus 16 equals 0. It's the same as finding the 4th roots of 16. Well, before we start, what's the real 6th root of or 4th root of 16? 2. So we better get 2 as an answer. And since this is an even root, 4 is even, what else would be a root?
4.
So if we take the square root of 16, we get plus or minus. So it should be negative 2, and we should get a plus and a minus 2 out of our answers. So let's do this. So first thing we want to do is write 16 in trig form. And I'm going to make this, we'll do this the easy way. There's the point 16. How far away is that from 0? 16. What is the angle there on the positive x-axis?
0.
Theta equals 0. So 16 equals 16 cosine 0 degrees plus I sine 0 degrees. That's our number in trig form. So the 4th roots of 16 is going to be the real 4th root of 16 times the cosine of 0 plus 360k over 4, because we're finding the 4th root, plus I sine 0 plus 360k over 4. And here k is going to be 0, 1, 2, and 3. Oops, I need one more parentheses. All right, so for k equals 0, we know the real fourth root of 16 is 2. Well, the cosine of 360 times 0 is 0 plus 0, 0 divided by 4 is still 0. We get the cosine of 0 plus I sine of 0. Well, what's the cosine of 0? 1. What's the sine of 0? 0. So one of the fourth roots of 16 is 2, just like we expected. For k equals 1, we get 2 times 0 plus 1 times 360, 0 plus 360 divided by 4. What's 360 divided by 4? 90 plus I sine 90. What is the cosine of 90? 0. Sine of 90? 1. So we get 2I. Now let's go back to thinking about solving equations. When we solve an equation and we get a complex solution, do you remember from Algebra 2 what else we're guaranteed as a solution? The conjugate, right? When we do the quadratic formula, we get plus or minus the square root. And if that square root's imaginary, we get the plus or minus I. So we should get the conjugate of 2I as well. So we should get negative 2I. So let's see if our suspicions are correct. And we want to be sure math is not lying to us. You know, I'll tell you, math doesn't lie to you. So now we're going to do 360 times 2, and we divide by 4. So that's 360 divided by 2. Cosine of 180 plus I sine 180. And what's the cosine of 180? Negative 1, the sine of 180? 0. There's our negative 2. And for k equals 3, we get 2 times the cosine of 3 times 360 divided by 4. 3/4 of 360. 270. Plus I sine 270. And the cosine of 270? 0, the sine of 270. And our last fourth root is negative 2I. And if you plug in your calculator 2I to the fourth power, you would get 16. Negative 2I to the fourth power, 16. And geometrically, if we were to plot these solutions, they show up on a circle. There's 2. There's 2I. There's negative 2. There's negative 2I. Each of these angles between the roots is 90 degrees, which is 360 divided by 4. The radius of this circle is 2. So we get our roots symmetrically distributed on the circle, radius 2. And the angle between each of those roots is 360 divided by 4. So we get this nice symmetry in the complex plane with the roots. All right, questions? All right, I wanted to look at one example where the angles don't turn out quite so nicely, just to show a slightly different example where these angles aren't quite as nice, but still the same procedure. We want the 3 third roots of 4 square root 3 minus 4i. So now we're not just finding the roots of a real number, we're finding the roots of a complex number. So the first thing, we want to write in trig form. So r is the square root of 4 square root 3 squared plus negative 4 squared. So this is 3 times 16, which is 48, plus 16, which is 64. Square root of 64 is 8. Theta, we're going to say tangent theta is negative 4 over 4 square root 3. So negative 1 over the square root of 3. This time it is negative 1. And what quadrant are we in here? X is positive, Y is negative. 4, fourth quadrant. So our fourth quadrant angle, whose tangent is negative 1 over square root of 3. So it's another pi 6 angle in the fourth quadrant. 11 pi over 6. And I'm going to do this in degrees. So 11 pi over 6 is 330 degrees. Just to make our lives a little easier here. So the third roots. Well, let's do the third, what's the real third root of 8? 2. So the third roots, we're going to get 2 times the cosine of 330 plus 360k, keeping track of those coterminal angles, divided by 3, because we're finding the third roots, plus I sine this whole angle. And here k is going to equal 0, 1, and 2. So for k equals 0, we get 2 cosine of 330 divided by 3. 110 plus I sine 110. And I plugged all these into my calculator, and I just got decimal answers. So this comes out to be negative 0.68 plus 1.9i is one of the third roots. For k equals 1, I get 2 times the cosine of 330 plus 360 divided by 3. That comes out to be 230 degrees. And again, what I did, 360 plus 330, divide that all by 3. Plug that into my calculator, and I get negative 1.29 minus 1.53i. And for k equals 2, I get 2 times the cosine of 330 plus 720, 360 divided by, or 360 times 2, divided by 3. That gives me the cosine of 350. And I calculate that out, and I get 1.97 minus 0.35i. And in your calculator, if you cubed those numbers, you would get this number. Yes?
So how would you cube it with the complex number, with the I?
I think most of your calculators have an I button,
Okay.
and you can just put it in. You can type it in just like that. All right. You have new powers in mathematics. You can take the roots of complex numbers. No pun intended. Is it, powers in mathematics, roots.
Yeah, I got it.
Yeah.
See you Monday. Just Monday? See you.
I bet you that some of those have like all the way to like R.
Mr. Beaver, why do you like assigning us so much homework?
What's that?
Why do you like assigning us so much homework?
Because we need the practice.
You're not wrong. Start at 109 or
1:30.
130.
Now, some of these problems, on the last homework, we didn't do any multiplication and division. So there's some just multiplication and division problems in here. No, this is homework. The review is separate. Yes. It just looks like a lot because all the most of the numbers are in the 100s.
It's still one.
Well, this is, what is this, like 5 problems? 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 problems? That's not bad.
Too many. Anything over 3 is a lot.
I 100% agree with that statement.
Was I talking to this class about